Hello everybody, and welcome to Notes 4.5. Today we are going to be talking about solving quadratic equations by factoring and the square root method. Let's talk about the square root method to begin with. So what we're going to do is we're just going to jump off and jump in with an example. All right, so solving using the square root method is a lot like solving the absolute value. So think back to when we were solving absolute value equations. Our goal was to get the piece of the equation with the absolute value bars completely by itself, okay? So when we got it completely by itself, then we could split it off into two equations. Well, square root method is similar to absolute value in the regards that we need to get the piece that's being squared by itself. We have to isolate the piece being squared. So right up here, I need to get x squared completely by itself. So I divide both sides by 9. That gets me x squared equals 25 over 9. Well, to undo the square, we're going to take the square root. So I square root both sides. Now remember, when you're solving and you put the square root there, your answer has to include the plus or minus. So, and then when you're square rooting a fraction, you take the square root of the top and the square root of the bottom. So I get plus or minus 5/3. Let's look at another one. So we have 2x squared minus 4 equals 92. So my goal is to get the x squared completely by itself. So I'm going to add 4 to begin with. Then I'm going to divide both sides by 2. And that gets me x squared equals 48. Well, to undo the square, I take the square root. Well, 48 is not a perfect square, so I'm going to have to see, does 48 simplify? So that is 2 times 24. I can't break down 2 anymore, but I can break down 24 into 2 times 12. I can't break down that 2 either, but I can break down 12. 2 times 6, and I can break 6 down into 2 times 3. So now I'm going to circle things that I have 2 of, because remember, a square root is something times itself. Something times itself. So there's a pair of 2's. There's a pair of 2's. Now, 2 different ways you can think about this. So you can say, well, you want to marry somebody who's like you. So that first set of 2's, they found somebody who was like them. They went into the radical as 2 separate 2's. They got married, but now they come out of the radical as one happy family of 2. Okay? Same with the other pair of 2's. They're 2 separate single people. They go into the radical to get married. They come out of the radical no longer single, but one happy family of 2. Another way to think about it is, well, 2 times 2 is 4. 2 times, so that would be like the square root of 4, which is 2. 2 times 2 would be the square root of 4, which is also 2. So that's another way to look at it. So I have, let me do some erasing because I wrote over my work here. Okay, so I now have plus or minus, and remember, we've got to put the plus or minus there because we put the radical there in the course of solving. So 2 times 2 is 4. So that gives me plus or minus 4 square roots of 3. Now, remember the 3 here, he didn't have anybody, whoops, wrong color. He didn't have anybody to pair up with. So since he didn't have anybody to pair up with, he had to stay inside the radical. All right, let's look at another example. All right, so 3x squared plus 4 equals 15. I'm still working with the fact that I've got to get x squared by itself. So I subtract 4 from both sides. I subtract 4 from both sides. That gets me 3x squared equals 11. I have to get 3 by itself, or excuse me, I have to get x squared by itself, so I've got to divide by 3. I must divide by 3. So that gets me x squared equals 11 over 3. Now, to undo the square, I have to take the square root. So I square root both sides. Now I square root the top and the bottom. And I'm like, well, that gives me x equals plus or minus the square root of 11 divided by the square root of 3. And it's plus or minus because we put the radical there. So, well, the rules of radicals say I can have square roots in the top all day long. Doesn't matter. Nobody cares. But I can't have a radical in the bottom. So I have to do something called rationalizing the denominator. Okay, rationalizing the denominator. You did this a little bit in geometry when you were working with your 30, 60, 90 triangles and your 45, 45, 90 triangles. So to rationalize the denominator, you take whatever radical is in the denominator and you multiply top and bottom by that radical, by that square root. Okay, so we had a square root in the bottom, so I multiply top and bottom by the square root of 3. Now think about it. The square root of 3 divided by the square root of 3 is 1. So we are just multiplying by a fancy form of 1. So now I just multiply the radicals together. Square root of 11 times square root of 3 is square root of 33. Square root of 3 times square root of 3 is square root of 9. But wait, the square root of 9 is 3. So that simplifies to be plus or minus the square root of 33 over 3. Now, we will talk about square roots a little bit more in the spring semester. This is probably the hardest you'll see until we get to the spring semester in terms of simplifying and rationalizing radicals. Okay, 2 more examples and then we're done with the square root method. So the first example is 5x squared minus 7 equals 65. So my quest is still to get the x squared term by itself. So I'm going to add 7 to both sides. Still looking to get x squared by itself, so I have to divide both sides by 5. Well, to undo the square, I have to take the square root of both sides. Now, the square root of x squared is just x. And because I put the radical there, I'm the one who put the radical there while trying to solve, I have to put plus or minus. Now, the square root in the top is okay. We can have square roots in the top all day long. Nobody's going to care. But where we do care is when we have a square root in the bottom. So I have to get that square root up out of the bottom. So I'm going to multiply top and bottom by the square root of 5. Now, if you'll recall, the square root of 5 divided by the square root of 5 is 1. So really, I'm just multiplying this fraction by a fancy form of 1. I'm changing what it looks like, but I'm not changing its value. I'm not changing who it really is. So now I'm going to multiply the tops. 72 times 5 is 360. And then square root of 5 times square root of 5 is square root of 25. Now, the square root in the top is completely okay, but we need to see if we can simplify it. So 360 is 2 times 180. 180 is 2 times 90. 90 is 2 times 45. Now, 45 won't break down any further by 2, but it will break down by 3. 3 times 15. 15 will break down to be 3 times 5. So because this is the square root, I have to circle in groups of 2. So 2 times 2, and then 3 times 3. Now, you'll notice that the 2 and the 5 right here, they didn't have anybody to partner up with. So they've got to go back under the radical. So the 2 and the 3 come out. So 2 times 3 is 6. The 2 and the 5 stay in the radical. 2 times 5 is 10. So I've got 6 square roots of 10. And then, of course, the square root of 25 is 5. Let's look at our last example for the square root method. X plus 2 quantity squared equals 36. Now, of course, if this had a variable in front of the parentheses and something being added or subtracted after the parentheses, your goal is to get the parentheses squared by itself. In this case, it's already by itself, but if it's not, you may have to manipulate things just like you did with the absolute value, but we've got to get the parentheses squared by itself. So we're good to go here. So now I go, okay, well, how do I undo the square? Well, I have to take the square root. So I take the square root of both sides. The square root of x plus 2 squared is x plus 2. The square root of 36 is 6, but remember, I put that there, so I have to put plus or minus. All right, now I'm going to solve for x. So I have to subtract 2. So I get negative 2 plus or minus 6. So what we're going to do now is we're going to simplify this. I'm going to do negative 2 plus 6, and then I'm going to do negative 2 minus 6. So I get 4 and negative 8. And there's my two solutions. Notice that I'm always writing my answers in solution set notation. You always want to use proper format. All right, so let's move on to factoring. Okay, let's talk about using a GCF to factor and solve. So we're going to start with the simple methods of factoring, and then we're going to build up to the more complex methods of factoring. So let's start with GCF. Now, you know, to factor and solve any quadratic, it has to equal 0. If it doesn't equal 0, you can't solve it. You've got to manipulate the equation and make it equal 0. So I am going to subtract 8x from both sides. So that gives me 5x squared minus 15x equals 0. Now, let's talk about using the GCF, greatest common factor. You want to look at the coefficients and then the variables. Don't try to do it as one big thing. Break it into tiny, manageable pieces. Now, let's talk about when you can pull a variable out as a GCF. The only time you can pull a variable out as a GCF is when every term contains that variable. If every term does not contain that variable, you may not use it as a GCF. So, let's look. So I'm going to talk about the coefficients first. What is the GCF, the greatest common factor of 5 and 15? Well, it's going to be 5, because 5 is the biggest number that goes into 5 and 15. Okay, so now we're going to pull out a 5. Let's talk about x squared and x. Both terms have an x, so I can factor out x as part of my GCF. Well, I have an x squared and I have an x. So what is the biggest variable between x and x squared that goes into x and x squared? Well, it's x. So the way I think about it in terms of numbers is for the coefficient, I pick the biggest number that goes into both. For the variables, I pick the variable with the smallest exponent. So if that helps. So I have a GCF of 5x. So I set 5x on the outside, and then I put what's left on the inside when I factor the 5x out. So when I pull a 5x out of 5x squared, I'm left with x. When I pull a 5x out of 15x, I'm left with 3. So you don't want to forget about the GCF. You've always got to write them just in case for some weird reason you had to multiply it back together. If you throw away that GCF, it won't multiply back to make the original problem. So now that we know 5x times x minus 3 equals 0, we can take and set each piece equal to 0. So I can say 5x equals 0 and x minus 3 equals 0. So now I say, well, how do I solve for x? 5x equals 0. I'm going to divide by 5, and I get x equals 0. Well, x minus 3 equals 0. Well, I'm going to add 3 to both sides, and that gets me x equals 3. So my solution set is x equals 0 and 3. Now, you always want to check your answer. Always. That is the way you can be sure that you're getting the solutions correct. So if I plug 0 in, obviously I'm going to get 0 equals 0. 3 squared is 9. 9 times 5 is 45. 45 minus 21 is 24. And 8 times 3 is 24. So it works. So you always want to check your work. Okay, let's talk about using GCF in combination with other methods to solve. So before we do anything, we know the rule. The rule is that it has to equal 0 to solve. Well, this one does, so check, one less step to do. Now let's see. Before you dive into any of the other methods, you always, always, always want to see, can I pull out a GCF? Because if you can pull out a GCF, your factoring is going to be so much easier, so much easier. So I look and I say, okay, well, they both don't have an X, so I can't factor out an X. But what's the biggest number that goes into 3 and 3? Well, that would be 3. So I'm going to factor out a 3. And that leaves me with x squared minus 1 on the inside. So let's look and see, can I factor that inside further? Well, let's go back to thinking about difference of two squares. So the criteria, the following 3 criteria have to be met for you to be able to factor it like a difference of two squares. Well, first thing, 2 terms. Check. Are both terms perfect squares? Well, I know how to make sure a number is a perfect square. It's something times itself produces that number, okay? But what about a variable with an exponent? A variable with an exponent. What would make a variable with an exponent a perfect square? Well, let's think. Well, what if the exponent was even? Just think about it. X times x is x squared. X squared times x squared is x to the 4th. X cubed times x cubed is x to the 6th. X to the 4th times x to the 4th is x to the 8th. So you get my idea there. If your exponent is even, your variable is going to be a perfect square. Now, where that gets a little tricky is if it has a coefficient other than 1 in front of it. So if you had something like 9x squared, you'd want to make sure that the 9 and the x squared are both perfect squared. But that's the only catch. So x squared, yeah, because that's x times x. 1 is 1 times 1. Okay, check. Both terms are separated by subtraction. Okay, there's a big subtraction sign. Check. Now, since the inside fits the above criteria, we can factor. So, I'm going to tell you how I've done it for years, ever since I learned to factor difference of two squares. And of course, if you go to another teacher, somebody else, they might give you a little bit different idea on it, and that's fine. We've all learned to factor difference of two squares thinking about different things. But the way I was always taught is, okay, so you take your parentheses that you're going to factor, and you set it up as 2 separate parentheses. One is plus, one is minus. Now, to figure out what goes in the first spot of each parentheses, you take the square root. So that's x and x, because the square root of x squared is x, and that becomes the first term of your parentheses. You then take the square root of the second term. Well, that's 1. Don't include the minus, just the number. So that's 1, and that's 1. And you're like, but wait, isn't that going to produce a middle term? Well, let's talk about it. X times x is x squared. The outer term is x times negative 1. So that's negative x. The inside is 1 times x. So that's x. So negative x plus x, well, that's 0. It goes away. And then 1 times negative 1 gives me negative 1. Okay, and that's how I factor the inside. So you also don't want to forget your 3 out front, because if you forget that 3 out front and for some reason you had to multiply this back together, you'd only get x squared minus 1. You would not get 3x squared minus 3. Okay? Now, I know you're probably thinking, well, why did I have to do all this? Why couldn't I just, solve it by taking the square root? You could. You could add 3 and divide by 3 and then take the square root. That's perfectly fine. But what if the instructions say solve by factoring? If the instructions say solve by factoring and you try to do the square root method, you're not going to get credit for that problem because you are not demonstrating to us that you know how to solve by factoring. So yes, this problem can be solved two different ways. You can solve it by taking the square root, or you can solve it by factoring. So just please be cognizant over what the instructions say. If the instructions say, hey, solve, then you can solve any way you want. But if it says solve by factoring, and again, if you accidentally take the square root, you're not going to get credit. So make sure you are following those instructions. Okay, so back to this. So we have 3 times x minus 1 times x plus 1 equals 0. So we're going to set each piece equal to 0. So I have 3 equals 0, x minus 1 equals 0, x plus 1 equals 0. Well, will 3 ever equal 0? No. So he's out of here. All right, x minus 1 equals 0. That's x is 1. X plus 1 equals 0. That's x equals negative 1. So I have 2 solutions. Now, I've given you 2 different ways to write it, and that's because both are correct. It's just a matter of personal preference. So you can say negative 1, positive 1, or plus or minus 1. Either answer works. All right, let's talk about using trinomial factoring to solve. Now, we're first going to review what happens if a is 1. And this is most of the factoring you did in Algebra 1. When you factor trinomials, your a was typically 1. You may have gotten into some other values for a little bit later on, but predominantly you factored when a was equal to 1. So, first thing we've got to do is we've got to make sure it equals 0 to solve. Does it equal 0? I don't think so. So we're going to have to make it equal 0. So we are going to subtract 6 from both sides. So that gets me x squared minus x minus 6 equals 0. Now, if you remember, when a is equal to 1, you just simply have to know and figure out what 2 numbers multiply to make negative 6 and add to make negative 1, because they have to multiply to make the c value and add to make the b value. So what 2 numbers do multiply to negative 6 and add to negative 1? Well, how about negative 3 and 2? Because negative 3 times 2 is negative 6. And negative 3 plus 2 is negative 1. So that gets me x minus 3 times x plus 2 equals 0. So now all I have to do is set each piece equal to 0 and solve. So I get x equals 3 and x equals negative 2. So I write those. Of course, you always want to kind of plug them back in and check. So 3 squared is 9, 9 minus 3 is 6, woohoo! Negative 2 squared is 4, 4 minus the negative 2 is plus a positive 2, and that equals 6. So I know I've got the right answers. So I write it in solution set notation. X equals negative 2 and 3. Okay, now let's talk about factoring by grouping to solve. Factoring by grouping to solve. First thing, always, does it equal 0? It does, so we don't have to manipulate. Now, here are the steps. The first step you want to do is you want to underline, which we're considering grouping, you want to underline the first 2 terms and the second 2 terms. Okay, now we want to factor out the greatest common factor of each pair. We want to factor out the greatest common factor of each pair. So, looking at 6x squared plus 4x, well, the biggest number that goes into 6 and 4 is 2. And I can also pull an x out because both of those terms have an x. So I'm going to pull out a 2x. So the GCF of that first 2 terms, is 2x. Now let's look at the last two pairs. So 3x plus 2. Well, I can't pull an x out. And the biggest number that goes into 3 and 2 is 1. And you know what? That's okay. You can have a GCF of 1 and still be fine. So here I'm going to say, okay, my GCF is 1. And it's important that even if it's 1, that you put that it's 1. You're going to see why here in just a second. So I pull a 2x out of the first two terms, and that gets me 3x plus 2. I pull a 1 out of the last two terms, and that gets me 3x plus 2 as well. Now notice how each term has a 3x plus 2. I'm going to now pull that common term out and see what I'm left with. So if I say, okay, my brand new GCF is 3x plus 2. So if I pull out the common factor, that gets me 3x plus 2. And when I pull a 3x plus 2 out of the first term, I'm left with 2x. And when I pull the 3x plus 2 out of the second term, I'm left with 1. Now, we just set each factor equal to 0, and we solve for x. So the first equation, I get negative 2/3. The second equation, I get negative 1/2. So those are my solutions. Let's do another. First of all, does it equal 0? Yeah, it does. So let's go through our steps again. We're going to underline the first two terms and the second two terms. Boom. Now we're going to GCF both pairs. So the GCF of the first pair, well, the biggest number that goes into 2 and 6 is 2, but I can also factor out an x. So my first GCF is going to be 2x. The second two, well, can't pull an x out, but I can pull out a 2 because 2 is the biggest number that goes into 2 and 6. But be careful here. If the term right in front of the second pairing is negative, you want to pull out a negative 2. So if there is a subtraction sign separating the first pair from the second pair, you want to make sure that your GCF is negative because you always want your leading term to be positive. So I'm going to factor out a negative 2. Okay, so again, remember, we're pulling out a negative GCF this time because we want our leading term to be positive. So I factor out a 2x, and that leaves me with x minus 3 on the inside. I factor out a negative 2 from the second pairing, and that leaves me with x minus 3. Now notice each pairing has an x minus 3. That's going to be my new GCF if you think about it that way, or my common factor. So I'm going to pull the common factor, like a GCF, out of both terms. When I do that, that leaves me with x minus 3, because that's my common factor I pulled out front. When I pull an x minus 3 out of the first pairing, I get 2x. When I pull an x minus 3 out of the second pairing, I get minus 2. Now, I'm looking at that and I'm saying, could I have factored that further? Yeah, I can. I can pull out a 2. So I can factor that further. Now, I don't like the coefficient stuck in the middle, so I'm going to bring it to the front. Now, you're probably thinking, well, what if you'd followed your own advice and pulled out a 2 in the very beginning? You can do that, just don't let it get lost in all the grouping and the pairing and everything. So I chose not to do that because I didn't want everybody to remember, hey, there's still a 2 GCF floating around out here. But you can most definitely pull out the GCF first and then factor the inside by grouping. That is perfectly fine. But like I said, I just chose not to do it on this one because I didn't want y'all to get lost and have a 2 floating around somewhere out there. So if you choose to do it the way I did it and then look and say, okay, can I factor anything further? Then you're still gonna end up at the same answer, regardless of if you pull a 2 out in the beginning or you pull it out a little bit further down the problem and factor that 2 out. It doesn't matter whether you, in this case, whether you factor it out at the beginning or you factor it out kind of somewhere down the road. All right, so now I've got 2 times x minus 3 times x minus 1. So I'm going to set each term equal to 0. Now, will 2 ever equal 0? I don't think so, Scooter. So we don't have to consider it. X minus 3 equals 0. Well, that means x equals 3. X minus 1 equals 0. Well, that means x equals 1. And of course, you'd want to check those, plug it back in just to be on the safe side, make sure you're correct. And you'll find out that both 1 and 3 work. So that's factoring by grouping. And you're like, well, how is that going to help me when A is not 1? So glad you asked. Let's look further. Okay, let's talk about how we can use the method we just learned, factoring by grouping, to help us solve a trinomial where A is not equal to 1. Now, you may be sitting out there and you may be going, dude, I can guess and check and get it. Do I have to use this method? The answer is no. This is just another method that if you have trouble factoring when A is not 1, this is just another method to help you factor complex trinomials. Okay, so check it out, and if it's easier for you, use it. If you're better at guess and check, use it. We're just giving you, like I said, more tools to put in your toolkit to help you with factoring. So the first thing you want to check is, does it equal 0? And it does. Next, we're going to assign A, B, and C. Now, this is standard form, so this is the A, B, and C of standard form. It's also the A, B, and C you use when you do the quadratic formula. So that hadn't changed. So here are the steps. The first step is we have to multiply A and C to find all the factors that multiply to make A times C. So A times C, well, that's 20 because 10 times 2 is 20. Now, I am going to list all the factor pairs that multiply to make 20. 1 and 20, 2 and 10, 4 and 5. Now, I'm not going to list the duplicate pairs this time because A times C is positive. If A times C is positive, then I look at the B term to determine the signs of both numbers in my pairing. Well, in this case, since B is positive, both numbers in each pair are going to be positive. If AC was positive but B was negative, then both numbers in each pair would be negative. Okay, so we know these all multiply to make positive 20. Now we're going to see, well, okay, great, they equal 20, but which ones add to make 9? Well, 1 plus 20, that's 21. Not close. 2 plus 10, that's 12, getting closer. 4 plus 5 is 9. So that's the factor pair I'm going to use. Now, I'm going to break that B term into 2 separate terms using the factors that I found from step 1. The order of these 2 terms do not matter. Okay? So I'm going to break 9x into 4x plus 5x. And this is what I was saying doesn't matter. It doesn't matter if you do 4x plus 5x or 5x plus 4x. And I'll show you in just a minute why. Okay, so now look, I'm back at 4 terms. I can do factor by grouping. So I'm going to underline first 2 terms, underline the last 2 terms. And then I'm going to GCF. Well, the GCF of 10x squared and 4x, well, that's 2x. The GCF of 5x and 2, that's 1. So now I pull 2x out of the first 2 terms and 1 out of the second 2 terms. Well, I see right here that my common term is 5x plus 2. 5x plus 2 is my common term. So I'm going to pull that out front, and that's going to leave me with 2x plus 1. Okay, now let's pause, hit the pause button, and let's say, what would happen if I had switched those? What would happen if I had 10x squared plus 5x plus 4x plus 2? Okay, so let's look at that. Well, underline the first two, underline the last two. My GCF would be 5x here. It would be 2 here. So I would factor out a 5x, and that would give me 2x plus 1. I would factor out a 2, and that would give me 2x plus 1 also. So as you can see, your common term is now 2x plus 1. So I factor that out, and that leaves me with 5x plus 2 on the inside. Okay, so as you can see, it doesn't matter if you do 4x plus 5x or 5x plus 4x. If your math is correct, no matter what you put first, it will all come out to be the same. Okay, so let me erase this. And now let's go back to our problem. Let's hit the pause and we'll keep going. So I'm now going to take each pair, set them equal to 0 and solve. I get negative 2/5 and negative 1/2. And I write that in my solution set notation. Okay, last example. So first thing we need to do is, does it equal 0? Yes! Okay, so now we're going to assign A, B, and C just like we normally do. Okay, so let's go through the steps. The first step is we're going to multiply A times C. So A times C is negative 15. Now, you'll notice that because AC is negative 15, I'm going to use the duplicate pairs. And you're going to see what I mean here in just a second. So, all the factors of 15. 1 and 15, 3 and 5, 5 and 3, 15 and 1. Now, you'll notice that by listing the duplicate pairs, if you then go and make the left one of each pair negative, then you've got negative 1 positive 15, but you've also got negative 15 positive 1. So you can manipulate the signs there. That just makes everything a little bit easier. So I know all 4 of these factor pairs multiply to make negative 15, but they also have to add to make 14. So let's try. Negative 1 and 15 is 14. Well, technically we're done. But for grins and giggles, let's see what the others would give us. Positive 2, nope. Negative 2, nope. Negative 15 and 1, negative 14. No, because we need positive 14. So factor pair number 1 gives us what we need. Now, you're probably asking, if something happens like this where the first factor pair makes it work, do I have to check the other 3? No. I was just showing you why they wouldn't work. But if you found your factor pair in the first pair, good for you. You can move on. So now we are going to break the B term into 2 separate terms using the factors we just found. The order does not matter. So you could do 3x squared minus 1x plus 15x, or you could do 3x squared plus 15x minus 1x minus 5. It doesn't matter. We saw that on the last slide. It doesn't matter. So I'm going to break 14x into 15x minus 1x. So now I'm going to factor by grouping and solve. So underline the first 2, underline the second 2. So the GCF of my first 2 is 3x. the GCF of my second 2, it would be 1. But remember, we've got this negative here. So instead of it being a positive 1, it's going to be a negative 1. So now I factor 3x out of the first 2 and negative 1 out of the second 2. And you'll see right here, they leave me with x plus 5. So there's my common term. So I'm going to factor it out front. And when I factor x plus 5 out, that gives me 3x. And when I factor out x plus 5, that leaves me with minus 1. Now I take and set each one equal to 0. Well, x plus 5 equals 0. That means x is 5. I mean negative 5. Sorry, my bad. X plus 5 equals 0 means x equals negative 5. Oh my goodness. Okay, so 3x minus 1 equals 0. That means x equals 1/3. So my solutions are x equals negative 5 and x equals 1/3. We can plug them back in to check them, which is always a good idea. And when I plugged them back in to check them, I found that they worked. So my solution says x equals negative 5 and 1/3. And that's it. That's it. That's the whole presentation. We're done. All right, so after you do this, you're going to go work on your worksheet 4.5. You're going to work on worksheet 4.5, and then that's it. All right, so please remember to be safe out there. Be careful. Wash those hands. Wear your mask. And be safe, be careful, social distance, 6 feet apart. Take care of yourself, stay healthy, and we'll see you back next time. Have a good one. Bye-bye.